Alright, derivatives of exponential functions. I'll address the with them in part 3 actually because what I want to do is get you aware of the meaning behind this. What does this mean? What does the math mean? So let's take a look at an example. We have a glass of cold milk from the refrigerator that is left on the counter on a warm summer day. Okay? Bad thing. Alright, so its temperature Y in degrees Fahrenheit after sitting on the counter in T minutes is Y equals 72 minus 30, all in parentheses, 0.98 T to the T power. Okay, let's look at that. First of all, let's see what the meaning of this formula is. We can ask ourselves, well, what was the temperature of the fridge? Well, the temperature of the fridge was probably the same as the temperature of the milk as soon as we took the milk out. That means that the time spent outside would be essentially zero, right? So if t is 0, then 0.98 to the 0 would be 1. Anything to the 0th power would be 1. So 1 times 30. So we have 72 minus 30. And let's look at that. So the temperature of the fridge, come on now, there it is. Temperature of the fridge is 72. It's essentially 72 minus 30. So that is 42 degrees Fahrenheit. And that's reasonable. Now what about the temperature of the room? How can we figure that one out? The temperature of the room well, the milk will be room temperature after it's been in the room long time. So let's explode this number to a billion, a trillion, and 0.98 to a huge number is essentially 0. Remember, it's less than 1, so any number less than 1, when the exponent is a huge number, it goes down to 0. It gets less. So, if this is essentially 0, 0 times 30 would be 0. So that would be 72 minus 0, which equals 72 degrees Fahrenheit. Okay. Now, we might want to ask ourselves, when does the milk warm up the fastest? Is it right after you pull it out of the fridge? Or is it after some time, you pull it out of the fridge and you think, oh, well, it doesn't matter. I don't have to rush to bring it back to the fridge. It doesn't lose its temperature right away, so you can wait some time, and then say a couple hours later it suddenly starts losing its how cold it is. It's warms up really fast. Okay, so let's look at this. That is what the derivative is good for, telling us the rate of change. The derivative would be dy, the derivative of y with respect to time would be 0 minus 30 times 0.98 to the t minutes times the natural log of 0.98. Okay, now we could simplify that, and that is about 0.606. It's negative. No, it's not negative, because the natural log of 0.98 is a negative number. So negative times negative is positive. Positive 0.606 times 0.98 to the t. This is the t. Alright. Now this is the change in degrees Fahrenheit. The change in degrees Fahrenheit per minute. That's what this formula represents. So now we can look at it and say, well, suppose we put a huge number for t. Now, let's start with a small number. If we start with 0.606 times 0.98 to the 10 minutes, let's try 10 minutes. It turns out that with t equals 10 minutes, we get a number of about 0.5 degrees Fahrenheit per minute. Okay. For t equals 2 hours, 120 minutes, we get an exciting 0.05 degrees Fahrenheit per minute. What that means is, as soon as that milk comes out of the refrigerator, it's losing a lot of its cold. It's getting warmer and warmer really fast, increasing by 0.5 degrees per minute at minutes. So it's increasing its temperature really fast, and then gradually to become room temperature. Say about getting it straight back. Hey, it's already out. It probably is warmed up a lot. So just give it to your kid brother while he's playing Nintendo. He probably won't notice anyway that the milk is warm.